Hello everyone. Thanks for attending to my session. I'm warning you, it will be very technical, very tough, so hang on. So we'll talk about low latency GCs. What I mean by low latencies, it means that we're trying to lower the post time. So who here already have some issues with GC post time? Yes, okay. So my name is Jean-Philippe BEMPEL. I work for Qteo. Qteo is a company that do ads retargeting. But before Qteo, I was in a company that do some trading, financial domain, fintech, and the goal was to route order from the investment bank to the market in less than 100 microseconds, no milliseconds. And so it was changing to have on Java, on the JVM, to have a GC with the pause. Minor GC's pause time is like 20, 30 milliseconds at best, and having some orders that would be routed in less than 100 microseconds. So I was keen to go to the low latency GCs like C4 from Azul, and then going to understanding how they can lower the dispose. So I'll present you in this session the technique for concurrent marking that is common for both algorithms that we'll see in this session. Shenandoah is the algorithm that we will see from Red Hat. Then we will see C4. It's a biggest part because I have more experience into this algorithm. Then ZGC, that's the newest one. And finally, we'll help you to choose between those three. So I assume in this session that you will understand how basics GC work. So marking, marking, moving objects, and sweeping. So here for concurrent marking, it's for when you have the application and a GC working together. So concurrent marking is not new. It's already used in CMS and G1 algorithm, but it's common for all latency GCs. In concurrent marking, we try to mark the whole object graph concurrently with the application. It's based on the tricolor abstraction and the snapshot at the beginning algorithm that we'll explain just in a few minutes. So let's take an example with this object graph. We have the GC routes on the top left, and we try to traverse this graph and mark those objects. So there is tricolor, three color, white, gray, and black. So when we begin with the GC routes, we mark this object gray. Okay, we have traversed this object, and then we will continue with all the children of this object. And we will mark those children. There is only one in this case, so we mark gray this object, and once we have finished to mark all the children of the first object, we mark it black. Then, recursively, we continue to traverse the graph. So for the second object, we go to the children and mark them gray. So as all children are marked gray, we can mark the parent black. And then all the other objects have no children, so they can be marked black. So the meanings of those colors is like black object is live object and white is garbage. So at the end of the algorithm, you have either black or white objects. So this white object is garbage. It's referencing an object, but no object is referencing this one, so this is garbage. So that's fine when you have a GC that is stopping the world, stopping all the thread from your application. do this traversal not concurrently. So they have no application that modify the graph, so it's very simple. But with the concurrent marking, we may have some issues dealing with the fact that you have the application that can modify the object graph. So modification of this object graph can be two. First one is new allocation during this marking phase. So for new allocation, you can deal with this problem by two things. Marking automatically this object allocated as lived. Okay, it's new, so it will be used. So we can consider as lived, and otherwise. All the allocation could be considered not at the current GC cycle, so they can be allocated in some addresses that will not be considered by the GC for this cycle. So as we are concurrent, we have issues to deal with. So we can miss object because the object graph is modified by the application as we traverse this graph. So the tricle abstraction gives us two properties for this. If the mutator is the application thread, store a reference to a white object into a black object, and if all paths from a gray object to a white object are destroyed. What it means with the example is if we have an object graph ABC and an application thread that trying to execute this code, though the concurrent marking is actually have marked the B object, so it's marking right now, and we are at the B object. The application thread executes and store the reference of the C object into the A object, so a white object referenced by a black object, and then we remove all the paths from a gray object to a white object. In this situation, we have an issue because we have no way to reach the C object, and this is not garbage. This is still referenced by the A object, the black object, but as the object A is black, we will not go through this object again because it was already marked and considered as lived, and the C object will be considered as garbage. So that's the issue that we need to deal with. So to resolve this, there is two ways. Snapshot at the beginning or incremental update. In this section, we will see the snapshot at the beginning, and incremental update will be, we will see this later. So for SATB, snapshot at the beginning, we introduce a pre-write barrier by the JIT. So it means that when we assign an object reference, before this assignation, so when you're writing the field for the destination, we insert some code. The JIT will insert some code to deal with that. So this SATB barrier is only active when we are in a concurrent marking. So we know that at the global state that we are in concurrent marking. So at that moment, this barrier is active. Otherwise, we'll skip this code. The pseudocode for this will be, okay, this SATB write barrier is active, and if the field of destination is different from null, then we'll enqueue the reference of the field and the reference that will be in queue, and then later processed by the GC thread or dedicated thread. So it will introduce overhead. This is a write barrier. The JIT will produce new code. That's an example of this code. So you have at the top the condition if the SATB is active or not, and then you have all this code plus a call to a subroutines. So this code is not your code; it's the JIT that and the GC that needs this code to bookkeeping and to make sure that we don't lose any reference during the concurrent marking. So this kind of a barrier. So that's the way we handle this with the snapshot at the beginning. Now we will dig into the Shenandoah algorithm. So this algorithm was introduced by the Red Hat around 2013. It's based on G1. So there is a lot of base code that is common with G1. And it's available on the OpenJDK build from Red Hat, but also now into the JDK from 12, but not from the build from Oracle. So if you get a build, an OpenJDK build from Oracle, starting from JDK 12, you don't have the Shenandoah, even if the Shenandoah is in the OpenJDK source code, because they don't support it. But all other builds are okay. Or you can also have this backport of Shenandoah for OpenJDK 8 from the Red Hat build. So Shenandoah GC oppose that most of the JVM GC is not generational. So they consider that the generational hypothesis is not always true. So they don't want to have the segmentation by generation. There is still an option for partial collection, though. It's region-based. That's a constant for all the low latency GC now, even for G1. That use a read barrier that called with the Devoxx pointer. We'll see how it works afterward. There is a concept of self-healing that we'll also encounter for all the low latency GC. It's the cooperation between the mutator threads, the application thread, and the GC threads. For Shenandoah, it's only for concurrent compaction. Compaction is the moving object to release a region. So, as I said, it's mostly based on G1, so the same mechanism, but for the evacuation that you see in G1, now it's done concurrently with the application. So they can move object as your application is still running. The phases of Shenandoah, we start with an initial marking, that is stop the world. So we just scan the GC routes, and then on the concurrent marking that we'll see just before, with the SITB style. So snapshot at the beginning to resolve all the issue during the marking. Then you have the final remark, and in this, that stop the world. In this phase, we'll catch up all the references that was included by the pre-word barrier, and to catch up with those and the modification of the object graph during the concurrent marking. Then we have the concurrent cleanup. So if a region is full of garbage, we can already clean up this region and reuse for a new allocation. So at that moment, we don't have to move objects from a region to another. So we can already get those regions back for a new allocation. Then the concurrent evacuation, that's the hard part, to move objects from a region to another as your application is still accessing those objects. A phase where we update references. We will start to update references, stop the world, very short, and then the concurrent update referencing. So we are updating all the references that point to the objects that are moved from a region to another. So we have to update all the references that point to the old object. And stop the world to sync all that. And a concurrent cleanup to release all the regions that were cleaned. So how it works for concurrent evacuation? Simple principle that G1, garbage first. We build a collection set and we sort by the garbage inside the region. We start with the region with the most of the garbage because there are less objects to move to another region. We evacuate those regions and release for reuse for a new allocation. This concurrent evacuation is done with the help of one read barrier, the Devoxx pointer, and 4 write barriers. So we've already seen that we have a pre-while barrier for the concurrent marking, and we introduce new barrier also to deal with the concurrent evacuation. So those barriers are in need to keep a two-space invariant. All writes that needs to be done into an object must be done in this object that is placed in the two-space region. So we have the region source, the from space, and the region destination, the to space. So if you need to write an object, into an object, it needs to be into the to space region, not on the from space. So what is a Brooks pointer? So all objects have an additional forwarding pointer with them. So it's placed before the regular object. That's a regular object with a header and your fields below. And we add a Brooks pointer on top of it. So every object have a new pointer added. And this Brooks pointer point into the old object, old way object, with into the header. So it means that at each time we need to access an object, we need to dereference the Brooks pointer to get it. It means that we have a memory footprint overhead. So every object, even if you have millions of objects, you have those 8 bytes to add for 64 bits. And also a throughput overhead because you need to dereference, need a memory access to get to those objects. That's for example, the JIT what emits for each access. So we compute an address of an object, and we get an offset to get to the Brooks pointer, and we dereference it to load into the R13 register. And then you can access those fields. So you have this line for every access to this to any object. What about the concurrent copy? When we deal to the concurrent evacuation, if it's done by GC thread, it's pretty simple. We have the from space and the to space, so the source of the region and the destination. We have an object. We have a GC thread that will get this object and move to the destination region. We copy the object into the to space, and then we update the Brooks pointer to point to the new location of this object. It means that if another application thread tries to access the object in the from space, it will dereference the Brooks pointer and get to the new location. That's the easy part. Now we have application thread that are trying to access the object in the from space. So two concurrent threads, application thread, that try to access to this object. As we have the invariant from Shenandoah, it means that all writes needs to be done into space. So we are just reading the object, so no problem. We just dereference the Brooks pointer and get to access the object and just read the fields into this object. It's still valid. Now the tricky part, writer's thread. We have two concurrent writing application threads that want to write into this object. It could be two different fields, but still we have the invariant that will be break like this because we are writing into an object that is in the from space. So at that moment, each of the writer's thread need to evacuate this object into the to space. So each of them will copy the object in two different locations. So each thread will copy the object. And then they both try to update the Brooks pointer concurrently. They use an atomic instruction for this, a CAS, concurrent swap instruction, and only one will win. So only one will correctly update the Brooks pointer. The other one will fail and will know that, okay, there is an issue with this operation. I need to reread the Brooks pointer and see that the Brooks pointer has been updated and use the new one to access the correct object, and the other copy of the object will be discarded. So one will really copy the object, update the Brooks pointer, and then the other thread will just follow the box pointer and write into the object at the correct location. So write barrier. Any writes, even for primitive, will trigger this barrier. So every write into an object that is in from space will be protected by this kind of code, pseudocode in Java. So if we have an evacuation progress, and if the object is in the collection set that we'll try to reclaim by the GC, and if the copy is not yet done for this object, we evacuate this object. Just the conditions are the right barrier. In terms of code, it will be like this. So JIT will also inject new code to deal with this. So every write will have this code. With the first two instructions is the condition for if we are in evacuation progress or not. And then other condition, and then we have also a call to a subroutine to continue and evacuate the object. We have also some exotic barrier. We have 4 write barriers, so we have 3 more. For pointer comparison, we need also to deal with this case. The compare and swap also, and the clone. In extreme cases, we have, with Shenandoah algorithm, a late memory release. It means that the region that we will release will be at the end of the cycle. So if the region is full of garbage, it will be released earlier, but for complete, if you have objects that need to be evacuated, you need to wait the evacuation and then all the reference updates for all the objects pointing to those objects that were moved. So the release needs is only happening at the concurrent cleanup phase at the end of the cycle. So we can have some allocation that overrun the GC because of the time to go to the end of the GC cycle. So we have failure mode. First mode is pacing. It means that we insert like a thread.slip into the allocation path for the application thread. So your application thread is trying to allocate. So the GC will slow you down to trying to keep up with the GC cycle, up to 10 milliseconds. The second mode is the degenerated GC. So it starts with a regular cycle, and then if we cannot keep up, it will stop all the application thread in a stop the world mode and finish the cycle with this stop the world phase. And then if you cannot keep up again, fall back to a regular full GC, parallel full GC. Now Azul C4. So C4 for me it's like this because my father was in the army. But C4 stands for Continuously Concurrent Compacting Collector. It's a generational algorithm with young and old, like you are used to. Again, region-based, but called pages. You use a read barrier, again, called Loaded Value Barrier, LVB. The self-healing concept, again, cooperation between immutator threads and GC threads at all levels. The original algorithm is poseless, but the implementation requires save points on the hotspot. The poses that you can experience with this algorithm is less than 1 millisecond most of the time. And so the LVB, it's a Baker-style barrier compared to the Brooks pointer. It means that when we move objects, we use a forwarding table that is aside of the heap. So it's in a native code, basically, in a native space. Sorry. And we use this address to forward to get a location of the objects that were relocated. It's applied at load time. It means that we load a reference and then we compare this barrier at this moment. So it's not when we dereferencing like for box pointer, it's just when we load a reference, we check if the barrier is broken or not. So this barrier is also to ensure that we have those invariants, that we have a mark through. It means that this subject that we are trying to access is marked for the current GC cycle, and if it's not relocated. So if those invariants are broken, we start a self-healing process to correct this. So if the object is not marked, we mark this object because it's live because we access this object. And otherwise, we relocate this object that need to be relocated and correct the reference that, again, if we need to reaccess this object just after, it will be fixed so we can access to the new location. It means this LVB is checked for each reference loads, but we can benefit from the JIT optimization to put this reference already checked into cache, like a register, and so we can have multiple access to the fields of an object, but only one check on this barrier. So this LVB, how it works, we are storing some metadata into the reference address. So we have 64 bits, it only works on 64 bits. And we store, because we have some spaces into this 64 bits addressing, we can store more information into this. So it's linked to every references. We store the LMT bit. This is not marked through bit. It means is this reference, is this object reference is marked or not, and the generation, because it's generational for this, so they store the generation into this reference address. This reference and then are checked again against the current GC phase through either thread local at first, so it means that we have almost always L1 cache hit, or by register for the newer version. So this is the kind of read barrier that we have with C4. So this is the version with the register. We just test the two registers. AR9 is the register that stores the current GC state. And then if it's okay against the reference address stored in AX, we can move on. Otherwise, we jump into the self-healing process. That's for the not marked through bits, but for relocation, there is another mechanism implemented with the VM memory translation from the virtualizing guest host translation, memory translation. They are using this mechanism to implement like a trap handler. So for Intel, it's EPT, extended page table, and for AMD, it's nested page table. So they use this to have a callback when we access an object that should not be. So like, it's like a page fault, but they insert a trap handler to correct it. I will just have a quick recap on the difference between virtual memory and physical memory, because we will see there is a trick with this in this algorithm. So virtual memory, 2 power 64-bit addressing, so it's very, very, very large. And physical memory, it's less, it's smaller, so 2 power 37, it's like, I don't remember, it's 16 gigabytes, something like this, whatever. So we can allocate a page into this physical memory and back by a page into the virtual memory. This is a 1-1 mapping. That's most of the time the way we are using the virtual memory and physical memory. But we can also allocate another page of memory backed by another page in virtual memory, but also another page in virtual memory backed by the same page, physical page, Okay, so we can have 2 pages in virtual memory backed by the same physical memory, but also have a virtual page that is backed by no physical memory. And when we access this, then we can decide if this is a page fault. We can decide if we need to get the memory elsewhere, like for example the disk. That's the way the swap is implemented. Okay. So C4 phases, classic, mark phases, marking all object graph, relocation, we are moving object from a page to another to release the pages, and the remap to update the old references, to update those references to the new relocated objects. But as we traverse the whole graph again during the remap phase, we can mark object again. So in fact, remap phase and mark phase for the next cycle are folded together. So as you see in this schema, we have the mark phase for the first cycle, relocate, and remap. And during the remap, we also done the mark phase for the next cycle. And go on. So we can shorten the time spent into the GC. So during this mark phase, concurrent marking, but it's used incremental update marking. This is a single pace algorithm. So no final mark or remark to catch up all the references that we may have lose during the process. And there is a self-healing notion that if we mark object that we are not marked during the current cycle. If you access an object, it's not marked, okay, we are marking it. So with this example, with the issue that we had before, we have an application set that executes this. It tries to store a reference into the black object. As we load the C reference, we trigger the LVB. And this triggering of LVB will go to C, and C is not marked. So we will mark then by the application thread. So C became gray, and we can mark all the objects correctly and without losing any object during the concurrent marking. So that's the way incremental updates will catch those objects. And then, okay. For the relocation phase, at G1, we select the pages that are most of the garbage, most of the dead object, garbage first, same principle. Then we protect the page that we want to evacuate. And we move objects from to the new allocated page. We build a side arrays with the forwarding information. So it's an heap table. And again, self-healing at that moment. As we have protected the page, if an application thread tries to access an object into this protected page, there is a trap, and the handler will fix by copying object to the new location and use the forwarding pointer to update and fix the reference that we are trying to dereference. So, with a schema, I have difference virtual and physical. We will see that it's important. So we allocate a new page in physical and virtual. We protect the page that we want to evacuate. So no more access without triggering a handler. We copy the object to the new location physically. We are installing forwarding tables to know where the object will be moved. We release the physical page here, only the physical part, not the virtual one. And we can allocate a new page to go to the next page. And this page will be backed by the physical that we just released. Okay, so with this principle, we just need to have only one page that is available to allocate and to start the cycle. So we can just have one page that is available, the last page of your memory that is available. Just need to do one to have all the cycle that's coming through, and we can releasing all the physical pages to reuse it immediately to continue the GC cycle. As the page is protected, every application thread that tries to access an object inside this page will trigger the trap and then trigger the move of those objects by and using the forwarding table to access to the new location if needed. For the remap phase, we traverse again the object graph and fix the references. We execute, the GC thread will execute all LVB for every object. And if the application thread is trying to access an object and the reference is not fixed, it will fix with the forwarding information. As we traverse again the object graph, we mark the object because we're accessing this object, so it's live. We mark for the next GC cycle. So at Criteo, we have a big Hadoop cluster, and in this architecture, there is a name node where all the metadata of the files are stored. So you can have files dispatched on several nodes into the cluster. But to know where those files are located, you have to have like an index, and it's stored into this name node. And we have a large cluster, like 2,000 or 3,000 nodes. So we need a very big heap, like 580 gigabytes. So we start on JDK 8 with G1, and it was very, very hard to tune because at some point G1 will fall back to a full GC, and on JDK 8 it's single-threaded with this kind of heap. It's like 30 minutes to when we have a full GC. So it's completely a showstopper for us. So we try Azul C4, the algorithm that we see. And since the rollout in production in October 2017, no issue, no GC issue since then. And the last, ZGC, so it will be very fast, no problem. The ZGC is currently non-generational, like Shenandoah, but they plan to do a generational GC. It's region-based also. They call it ZPGs. They are dynamically sized. They have the concurrent marking also, compaction, and ref processing. So ref processing is to deal with reference like weak, soft, phantom, and finalizer. So those are generally done into a stop-the-world phase, but if you are using a lot of weak references, they could take time and have a large pause time increase by this processing. So ZGC try to take out this ref processing into a concurrent mode. They use the color pointer, so something similar to C4, and the read load barrier. Again, that's an example of the load barrier from ZGC. They are using the thread local, so it means that we have an access, in memory access each time we try to load a reference. Again, the self-healing concept, cooperation between imitator thread and GC threads. Starting from JDK 11, so it's available since 11 with the experimental VM options. There are some improvements in JDK 12 with the class unloading, concurrent class unloading. And there are more also coming for JDK 13. And if you study a little bit this algorithm, it looks very, very familiar. So who knows about cliff click? Who knows is cliff click? Some couple of hands. Cliff Click was the original JVM JIT architect. He moved to Azul C4 to work on the JIT for Azul JVM and the C4 algorithm. So he knows about the C4 algorithm, and when he looked to ZGC, he said, wow, that's very, very similar. And in fact, it's very, very similar. So all the algorithm that we describe in C4 applies basically for ZGC. So basically it's done. So there is a couple of differences that we'll see. So the phases of ZGC, we have the initial mark against of the world for the GC routes. Then the concurrent mark again, classic, and the remap again folded with the concurrent marking. So the update of the references are done with the marking of the next GC cycle, like for C4. A final mark to sync. Concurrent prepare for relocation. That's the part where you can process the special references like weak, soft, phantom concurrently. They sync for starting the relocation phase. The concurrent relocation phase happens at that time, and then we cycle to the initial mark again and the remap. So ZGC use also color pointer. We store metadata in unused references. They use 42 bits for addressing currently, so it means that the heap size will be maximum 4 terabytes. And use 4 bits for metadata, mark 0, mark 1, remapped, finalizable. That's from the source code, you have this kind of documentation. So as you see on 64 bits, there is plenty of space at the end. There is a lot of zero that are still zero because they are not used for addressing. So they use 42 bits for the addressing, up to 4 terabytes, and the 4 metadata bits here. They, I think for JDK 13, they will increase this limit to 16 terabytes using 2 more bits. Still, we have some space. Also, they use a particular trick about multimapping. So when you use color pointer, you have those metadata that are stored into the reference address, and you need to the reference to the correct address, you need to unmask those metadata. So some hardwares have some support in as an instruction, the native instruction to unmask directly those addresses, like for Spark and ARM64. But for x86 on Linux and Windows, you have an override with classical instruction. So how to work around this problem? We can also consider that we have only one view is active at any point. It means that depending on each bit is active, only one bit is active for each state at the same time. So we can leverage this, and also the fact that we have plenty of virtual space. The 64 bits addressing virtual space is very huge, and we only use a small part. As you see, there is plenty of zero in the address reference. So they can use a trick with the virtual memory. We can have one physical page backed by multiple virtual page, and each virtual page have metadata active at one time. Okay, so depending on the phase of the GC, we can use this one or this one or this one, but still we are referencing the same physical pages. Okay, so depending on the GC phase, we can use an address with this one mark bit, and we are differencing this with this address through this physical page, or for the next cycle, this one bit, and we are differencing and go to these same pages, or if we are at the remap phase, we have this bit set, and we can dereference to get to the same physical page. So they are using more virtual memory, but we have plenty of this, and we can have this trick working correctly. So what is the difference between C4 and ZGC then? The way they are handling the remapping. C4 uses the protection, memory protection plus the trap handler. For that, they use and mask the color pointer. For unmasking the reference addresses, because they are storing those into color pointer, for C4 they use a kernel module. So when you install the Zinc JVM, you need to install a kernel module that deal with all the memory. And into this kernel module, they also use it to alias the address to go to the correct physical page. For Z, they use a multimapping, as we already see just before, or the hardware support. For page and relocation, C4 use a page that is fixed, matched with the host size because of the memory protection. And for relocation of the large object, so if you have a very, very large buffer, it's very expensive to move and relocate those kind of buffer. So C4 use it by remapping, so again, playing with the virtual and physical mapping. So physically they are not moved, but they just moved virtually by using another page that will map into this physical. For ZGC, pages are dynamic. They can be large as 100 megabytes. And they choose to have no relocation for those large objects. So it's like for G1, they are considered as humongous objects, or they are not moved. So how to choose from those GC algorithms? So if you have to run on Windows, there is one choice, Shenandoah, actually. If you want a battlefield-tested GC, it's very mature, you can use C4. I'm using C4 since 2012 in production. Shenandoah is also production ready. A little bit less than C4, but still production ready. If you want to minimize pauses, except the GC, if you want to, because there is other pauses in the JVM beside the GC, you can use C4 because it implements also the concurrent class unloading, concurrent ref processing, concurrent deflation, and other. ZGC because they also implement these kind of things, concurrent class unloading and concurrent ref processing currently. If you don't want to pay for this kind of GC, Shenandoah and Z, because C4 is, you need to pay a license. Those slides, I will tweet those slides, so we'll get all the references that I put into. So if you have the GC basics, you have some references that I put inside. For Shenandoah, you have some presentation and the wiki. For C4, you have the papers published about the POSES GC algorithm from 2005, the C4 implementation for x86 since 2011, some article about this version, and the 2010 version, source code version of the Azul. So it's a bit old now, but for the basic of the algorithm you can dig into. And for ZGC, some article and some presentation also. And a discussion about the difference between C4 and ZGC. And thank you for attending my session. Sorry, it was very technical. If you have questions, you have 30 seconds. Okay. Thank you.